So in this video, we are going to discuss how to prove the correctness of a compiler, or how to say, in what sense a compiler or optimizations will be correct according to the semantics of the programs. So in addition, we are going to review the CS420, which is the programming languages, in a little bit. So because all the theory of this compile correctness really depends heavily on the theory that is built in this program languages courses. So I'd like to start with the definition. So as I said in the previous video, we really need to make sure that each optimization should guarantee semantic preservation, or the target semantics the semantics preserved via optimization from a source to target. So source and target are two programs, and let's say that target is the result of a compiler when the source S is given. So let's say that C is a compile function and S is a given program, which is source, and T is a target program, which is the result of this compilation. And the semantic preservation is actually written like this. The semantics of the target is a subset of semantics of source. So it is a very dense statement, so we are going to discuss the meaning of this in more details. And the first thing to discuss is that what is the semantics of this target? So what is the target code's formal semantics? So let's say it is represented as a set of behaviors. So let's say that you have a program and it non-deterministically chooses a value, an integer value, say, and it is going to print it to the screen. Then it has many behaviors. One behavior is printing 0 to the screen, and another behavior is printing 1 to screen. Another is printing 2 to screen, printing 3 to screen, printing 4 to screen, etc., etc. And it is actually having an infinite number, not infinite, it is having many behaviors that is printing an integer to the screen. So as a result, the target in this code, formal semantics, should be represented as a set of behaviors. The source is the same thing. The source is also a program, and let's say it non-deterministically chooses a string, and then it is going to print a string to the screen. Then its formal semantics has many behaviors: printing A, printing AB, printing 42, printing 663, etc., etc. So it has many behaviors, and as a result, a code formal semantics should be represented as a set of behaviors. So target is also a code, source is also a code, and all the code's formal semantics is represented as a set of behaviors. And let's say that these double brackets are the semantic function which is given a program, and it is representing the set of behaviors that is corresponding to the given code. Okay, and now semantic preservation requires that the set of behaviors for a target program is a subset of the set of behaviors of the source program. So yeah, in other words, if a behavior is allowed in the target, for example, if printing 42 is allowed in the target, it should be also allowed in the source as well. So that is basically the meaning of this subset relation. The behaviors for the target is the subset of the behavior of the sources. In other words, if a behavior is allowed in a target, then it should be so in the source as well. Now we have a few questions now. So okay, this is a high-level theory of this, but we need to have a few concrete contexts for this statement. The first thing to discuss is how to define the set of behaviors for target and source programs. So let's say that T is an assembly program and S is a C program. Then how to get the set of behaviors from the syntax of this T and the syntax of this S, syntax of an assembly program and syntax of a C program. How to get the set of behaviors from these syntaxes? That is the first question, and we are going to visit this topic in the next slide. And the second thing is okay, let's assume that we have defined the semantics of the target and source code. Then how to prove that actually the target semantics is a subset of the source's semantics? We really need to have a theory about proving this equation. So we are going to learn what is called a simulation relation, which is actually doing so. And the final question is why we are not mandating that the target and source has the same semantics. So we are mandating that the target has a subset behavior than the source program. Why not equivalent? So the main reasons are the two. The first one is that the compiler may choose the outcome for a non-deterministic program. So for example, your C program is randomly choosing a value and it is going to print that to the screen. Then actually, all the properties, all the values satisfy the source program's specification. So maybe the compiler may choose 0 out of many possibilities and print 0 always. And actually, it should be allowed in the compilation because the actual in the real world, C and C++ and other languages compilers do such a thing all the time. Something non-deterministic in the source code can be determinized. So one value can be chosen from among many possibilities in the real-world compilers. So that's the reason why we require that the target semantics should be the subset of the source semantics. So another example may be evaluation order. So suppose that in C you have E1 plus E2. Then you may guess that E1 should be evaluated first, but it is actually not the case. So C doesn't define the evaluation order of E1 and E2. And in many compilers, actually, they choose to compile E2 first. I'm not sure why, but they do that. So as a result, the result of an expressions a result of E1 plus E2 can be many, depending on the evaluation order. But on the other end, in the assembly program, usually the evaluation order is fixed. You're going to evaluate E1 first, or you're going to evaluate E2 first. So in either way, evaluation order is fixed, so there will be no non-determinism related to the evaluation order. And as a result, the semantics of this target program, which has a fixed evaluation order, should be strictly less behavior than the behavior of the source program, which may choose the evaluation order from the source program. So that's the reason why we are going to require the subset relation instead of the equality for the definition of semantic preservation. And the second reason will be that subset is actually sufficient for what we usually want for compilers. So usually what we want from a compiler is that if you analyze your source code and it is okay or it is good, then the property should be preserved to the target as well. So for example, you were very diligently proving the fact that your source code will not crash at all. And then what you want from a compiler is that your target program that is generated by compiler from the source code should not crash as well. So, but in order to do that, what we really need is not the equality. Subset relation is sufficient because if crash is allowed in the target, it should be so in the source as well. Conversely, if source never crashes, then the target never crashes as well. So that's basically what we want from the compilers regarding the properties of the source code. So that's the reason why we require subset relation instead of the equality. And let's move on to explaining these two things: the how to define the semantics of the programs and how to prove the inequality of these semantics by simulation. So the semantics of a program is defined using what is called a labeled transition system. So here, a program is represented as a labeled transition system. And here, the node is a state, and transition is an execution possibly with an event. And for example, if you have a program and there is a line that is saying a print 42, then you are going to move your program counter and print 42 to the screen. So that's a behavior. And in that example, E1 will be, for example, printing 42. And this is the state, program state, where the program counter is pointing to print, the print 42 lines. And this next state will be the state that is whose program counter is pointing to the next line of the print 42. So this is basically a state, program state, which consists of, for example, program counter and the register files and the memories, etc., etc. And this is the interaction between the program and the outside world. For example, printing to screen, printing 42 to screen, or reading some value from the screen. And in this representation, there will be initial and final nodes. So initial nodes will be the program's initial state. For example, in C, you are going to start from the main function. So the main, right after initializing the main function, it will be the initial state from the given C program. And final node will be the final state of a given program. For example, returning some value from the main function. So that is the final state, basically. And behavior is a transition trace of this labeled transition systems. For example, from the initial state here, you can move to this, then maybe then one trace can be a possible behavior. You can do other traces as well. You can go to this, and immediately go to the final state. So this is also a possible behavior of this given program. So there can be even infinite traces as well if there's a loop. For example, you can start from here, and go on loop on it. So it is corresponding to the server program that is not terminating at all. So it is a possible behavior of a program as well. And now in the behavior, you will ignore all those transitions that are not labeled with event because they are not interacting with the outside world, and you're only collecting those events in the traces. So if it is going from this to this to this to this to this to this, then the event will be E1 and E2. So this will be the behavior of this trace. And you're going to collect all possible list of behave the event. A list of events will be a behavior, and the set of behaviors will be the set of list of events, basically. So this is the behavior of a given program. So for example, in the initial program state, you can, for example, write to the register and print to screen again, and read from the register, and read from register, and that's done. So it can be a program. Reading from the register and writing to the register is ignored because they are not interacting with the outside world, and we cannot observe the internal state of this program. So recall that in the previous video I said that even though optimization changes some characteristics of the execution, for example, the memory usage or the value of the registers, it is still that the optimizations are correct, and formally it is because we are going to ignore such variances. We are going to ignore the differences in the register values or memory values because they are not meant to be visible to the outside world. Okay, and the semantics is the set of the behaviors or set of the list of events that is possible from the transition traces. Okay, so far so good. And here's an example. C state is basically a memory plus a list of stack frames, and you're going to transition to the next states by manipulating the stack frames. And if the current program counter points to an arithmetic instruction, then do it. If it is pointing to some local allocation, then we're going to allocate it in the state, etc., etc. Assembly states and steps are much easier because assembly has a memory and register file, and that's all. And register set is also including the program counter. And a step in the assembly program is actually executing the program counter's instruction. So that has a much simpler semantics than the C programs. So you may know that actually the CPUs are not constructed in this way. It may have a large instruction pipelines and very large depths of the schedulers or something like that, but we don't care about this. The specification of the CPU specifically say that it is working as if it is a single set of memory and register file, and it is executed as if one instruction is executed at one time. So that's all we need to know about the semantics of these assembly programs. Okay, let's move on to how to prove the semantic preservation from a source to a target. And we're going to say there will be, let's say that source and target looks like this. So let's first ignore all the colors, and this is the initial state, and it can go to this, to this, to this, to this, to this, and it has the trace of E1 and E2. And there are many other possible traces as well. And in the target, it also has a very similar trace systems as well. So it can go to this, to this, to this, to this, to this, and whose traces have event E1 and E2. And they have the same event traces, actually. And you can see that the target's behavior should be a subset of this because all the possible traces the graphs are really similar, and all the possible traces can be simulated by the execution here. So, for example, if you have this path, then here you can do this path, which has the same events traces. Then how to prove this? How to formally argue the similarity of this graph? The answer is what is called a simulation relation. the first thing to do is relating target and source states. So you are relating this to this, this to this, this to this, and a node in the target with the node in the source with the same color, basically. So this color is basically representing what is called a simulation relation. So you can arbitrarily choose a simulation relation. So in the proof, you can choose anything. So if there is any valid simulation relation, then you can prove the semantic preservation from source to target. Okay, so far so good. And for a relation to be a simulation, we need to actually prove that a target step is simulated by a source step, which means that, okay, let's say we are in a target state. For all target state, let's say this. For all transition from this, let's say this is transitioning to this. And this step from the purple one to the yellow one should be simulated by the source program, where there is a corresponding purple node here, and it should have the same edge with the same label that is transitioning to the same color. So that is basically the simulation. So for our transition here, and for all state that is related by the simulation relation, so this purple is related to here. There exists a transition from this purple one to a yellow one, which is corresponding to this, which has the same label, same event here. It is satisfied because this edge is simulated by this edge. This edge is simulated by this edge, etc., etc. And this edge and this edge are simulated by this edge. This edge is simulated by this edge. This is simulated by this, etc., etc. So all the edges here are actually simulated by an edge in the source program. So that's the reason why the source and target are simulating, and target semantics is simulated by the source semantics. And actually, this proved by something similar to induction. So it's similar to induction. All steps are simulated here. So that is basically the key idea, key proof strategy for proving an inductive statement. But the trace can be infinite. So in such case, we need to use what is called a co-induction, which takes into account the possibility of the infinite traces. But we are not going into the details of this co-induction. So let's just ignore the third line, and let's say that what is important here is each target step is simulated by a source step. That is the definition of a simulation relation. Okay, so and then we can immediately say that all the possible traces here. So suppose that each target step is simulated. Then what we know about this program is that all traces can be simulated by a trace in the source with the same event labels. And as a result, we can say that all target behaviors are actually a source behavior, because all traces are simulated here with the same event traces. And as a result, we can prove that each target behavior is also a source behavior, which is the exact meaning of semantic preservation. And we can use this to the proving of the compiler's correctness, where compiler consists of multiple passes. For example, it first performs IRGen, and the simplify CFG, and mem2res, GVN, and data-coded elimination, and later assembly generation, etc., etc. And what we need to do is actually we need to establish the correctness of each pass instead of the entire compiler at once. The reason is that let's say that P0 is given to first pass and P1 is given, and it is given to the second pass and P2 is given. And let's say that P2 is given to the last pass and it is giving P3 back. So the source program P0 is transforming in multiple passes to the target program P3. And we don't need to establish the semantic preservation from P0 to P3 at once. It will be very difficult because the compiler is consisting of multiple passes. But what we need to do is actually proving each pass's semantic preservation. P1, which is the target of this pass, will have the less or equal semantics than the source of this optimization. And P2 semantics is the subset of P1 semantics. P3 semantics is a subset of P2 semantics. We can only prove all these three. Each pass preserves the semantics. So if this is proved, then we can just mix them all together into this statement, which says that the final target semantics is a subset of the initial target semantics, which is the final statement of the compiler's correctness. So we can do that because we can compose this subset relation safely. So that's the reason why we can prove each pass's optimization's correctness separately. So we can argue the correctness of Mentourage, GBN, that code elimination, and simplify CFG separately, and compose them to argue that entire compiler is actually correct. Entire optimization passes are actually correct. So this is usually called a vertical composition because a program is vertically traversing multiple optimizations, and you can compose the vertical. You can vertically compose each pass's compilation correctness results. And this is a purpose proof, and there is also a horizontal composition. So if you compile two files, for example, if you compile A.C and B.C, and want to compose the correctness of these two. So this is another dimension of compiler verification. And even you may want to employ a more powerful simulation that is capable of more semantic preservation. So I'm not going to go into the details of all these techniques, but I'm just saying that there are possible generalization of these compiler verification technologies. And we may want to verify some realistic compilers that is already verified realistic compilers like Concert or KKML. Concert is a verified C compiler, which has a lot of optimizations. And KKML is also optimizing ML compiler. And we may want to verify mainstream compilers. There are a few results about this. If you're interested, actually, I did one of the most important work in this area. So if you are interested in verifying, for example, LLVM, please contact me. And actually, we can verify compilers for more advanced topics like concurrent programs. So actually, we are actively working on this, verifying compilers for concurrent programs. So if you are interested in both compilers and concurrent programming, you can do such a research like this. Okay, this is basically a recap of CS420, the PL, and the compiler verifications.